Okay, thanks, Paul. Hi, everybody. Looking forward to this. In the next hour, we're going to solve a structure by SAD phasing. Let's first look at a little bit of the big picture about experimental phasing and model building. And then what we're going to do in this session is I'll give you a little bit of lecture, but before each lecture, we're going to do something. And so, for example, the very first thing we're going to do is we're going to do a little experiment to plan a SAD experiment. And we're just going to do that in the Phenix GUI. And then I'll explain how that works. And then you can ask questions about it. And then we'll do the same thing for solving the structure, finding the sites and everything using Autosol. Okay, so let's try this. So if I can make my presentation, here we go. So let's imagine that we're going to try to solve a structure by SAD phasing. And so we're going to have crystals. And those crystals have to have some anomalously scattering atom in them that we're going to try to find. And those site has to have a limited number of sites. And for example, selenomethionine is a great way to do this. And probably most of you that have solved structures experimental phasing use selenomethionine to do it. So we grow protein, we have E. coli or produce protein with selenomethionine, substituting the methionine sulfurs, and then those are going to be incorporated into our crystal, and we're going to find their locations. And so then we're going to collect anomalous SAD data. So we're going to go typically to a synchrotron, and we're going to collect data typically at the absorption edge of whatever the element is that we're looking for, in this case, selenium, which case we might go around 0.9792 angstroms to collect that data. And then we're going to process that data. We won't go through that today, but then we're going to locate where the selenium atoms are located. And we'll talk a little bit about that. And then we're going to calculate a density map. And then we're going to improve that map with density modification. And we will talk about that. And then we are going to build a model. Okay, so before we actually do this experiment, maybe we could do a little bit of thinking. And in particular, we could think about, is this going to work? So let's try to answer that question. So let me turn off this slide if I can. Okay, and now I'm going to open up Phenix.
Okay, so we're going to go to experimental phasing, right?
Experimental phasing, and then we're going to do planned SAD experiment.
So this is the fourth thing on the list under experimental phasing. So you should see a window like this open up.
Great. And so the idea of this is a little tool that will tell us, that will simulate a SAD experiment with varying degrees of accuracy in how accurately collect the data, and varying numbers of sites, varying the resolution, varying the ratio of the sites to the number of residues in the protein. So what we want to do is, so our first question is going to be, okay, let's suppose we had a crystal that contained 2 seleniums and 200 residues, and we collected it to 2.5 angstroms resolution, and we collected at the peak of selenium absorption. Would we expect to solve the structure? Okay, and so let's just do a little participant quiz on that one. Let's just see how many people think real quick. So click on participants, and Paul, can you clear the previous one if you already didn't?
No, it's, wait a minute, just let me clear. Okay, cleared now.
So here's our question: 2.5 angstroms, 200 residues, 2 seleniums, collected at the peak. Will we solve this structure? Okay, so just a yes or no. Is this a slam dunk? So let's click on participants and give ourselves an answer. Everybody's vote on that one real quick.
It's about, well, the yeses are winning.
The yeses are winning. Okay, so let's do our simulation now. Okay, so Paul, if we can type in our job title, something like that's what we're going to try to do. 2.5 angstroms, 200 residues, 2 seleniums. Will it work? And I want everybody to get used to using this little job title thing here. And the reason to put something in there is that it's not for now, right? It's for later when you can't remember what you were doing or why you did this little particular run. So with Phenix, you can do a lot of runs and you can end up with hundreds and hundreds of these things. And so it's a good idea to type something in there to remember why you're doing it. So can you make your screen bigger? No, Paul can't do that, Monica, but if you go to view options on the top of your screen, you can make Paul's screen bigger. You can make it like 100% original size, which is what I would recommend trying. And if you're on a phone, you can just do it with your fingers and make it bigger. Okay, actually I wasn't watching what Paul's doing. Okay, great. So Paul's typing some stuff in there. Anomalously scattering atoms, selenium, yep. And 2 of them, resolution 2.5, wavelength, let's put in 0.9792. That's the peak of selenium. Doesn't have to be exact. And we don't have to tell it other things. Number of residues, you do want that one, 200. And chain type is going to be protein here. Okay, that's great. That's all we need to tell it to do this little test. Okay, so we can hit run. And it just takes a second to run. When it's done, when it's done, you click on result. The result button is generally going to show you the things you want to look at afterwards. Yeah, so let's click on result, Paul. That's perfect. And notice that the result tells us a little bit about what we told it. Data set characteristics, target anomalous signal 30. And that's like, we'll get to that a little bit later, but that's what we're trying for. We're trying to get a high anomalous signal. And we have 200 residues, a protein, solvent fraction 0.5, that was just guessed. Atoms 1628, that was guessed from how many residues. Anomalously scattering atom, selenium, wavelength 0.9792, we typed that in. And then the F double prime, that's looked up from a table based on the wavelength we typed in. So F double prime is 3.8 and resolution 2.5. Notice it says B value. So we didn't tell it that, and it's just guessing that for us. B value for anomalously scattering atoms of 44. And what it did there was it said, oh, this is a 2.5 angstrom data set. That means that typically the atoms in our structure are going to have B values around 25. And the anomalously scattering atoms usually have a little bit more. Yeah, so what about the selenium white line? And actually, that's where we're collecting. And 3.8 is kind of a typical number for what you're going to get there. And so this is actually using that value. But that's going to depend on exactly the setup of your synchrotron and exact wavelength you have. Okay, so now what are the results of our little analysis? So it says targets for an entire data set and likely outcome. And notice that under this table, it says note target anomalous signal not achievable with tested iris sigma for resolutions of 5 angstrom and lower. And so that means that it's just noting for us that if you collected data to 5 angstroms here, it was definitely not going to work. Okay, so then the next line actually is going to go through exactly what I would say about this table. And I'm not going to read it, but I'm going to go through the exact same thing and notice that if you wanted to like see interpret how this table works, it interprets it for you right there. Okay, so let's look at the line that says 2.5. Paul, can you highlight that line, I think? Yeah, there we go. Okay, so that's what we were checking on. Okay, so if we go to 2.5 angstroms, the number of reflections is N. And so this would be a typical number of reflections at 2.5 angstroms for a structure that has 200 residues, would have 7,000 to 2.5 angstroms. And now this says, the next thing says 37 for I over sigma of I. That's saying to get what we want, we would have to have an overall average I over sigma of 37, which is a pretty high number. And that translates into a sigma of F of about 2.5%. And if we collected data to that accuracy, then we would expect, notice Paul was sliding over that. You can make these columns move in these tables in the results sections if you want by dragging them. So if you did that, and if you then split your data into 2 half data sets and you calculated the correlation of anomalous differences between the 2 half data sets, you'd expect it to be on the order of 0.4 or something. And that translates into an estimated actual accuracy of anomalous differences, their correlation to the true answer of about 0.56 or 0.6. That translates into an anomalous signal that we'll see a little bit later of 30, which is a very high number. And that translates into a probability of solving the structure of 99%, which is, as you all guessed, very good. Okay, and then the last column is, if you found the sites, you would expect the figure of merit of phasing for this structure to be about 0.4. And that's a very high number for a SAD structure. So that's about as good as it can be. And in fact, we're going to do this and we're going to see that's pretty much the answer. Okay, so now we're going to see what happens if we have a slightly different situation. Before I do that, let me just check. Are there any questions right now? Did anybody ask any unanswered?
There's a couple of questions actually. One is, how do we know which fields are mandatory?
Actually, in this particular GUI, it's not obvious. We don't tell you that. Most of them, we try to tell you like with parentheses or the word optional. So this one, I don't think you would know just by looking. Actually, though, Paul, can you hover over solvent fraction, for example? That'll be instructions, and it might tell us optional. Yeah. Okay. So then you'd be a little bit lucky, and it would just tell you that it's optional. Okay.
Yeah. Others? Then there's a couple of other questions. How do we plan experiments in the case of soaking?
How do you plan experiments in the case of soaking? Yeah, that's a great question. And the answer is we're going to kind of guess based on how things typically work. So this little program will try to do that for you. So if you put in something like I for iodine, and you then the typical number of sites for when you soak is going to be something like 1 per 20 to 1 per 100 residues, just ballpark. And so then you can put in numbers like that and it will guess reasonably for you. Let's see. And let's see. So soaking, and also soaking, of course, depends on the atom. So some things that you soak, you kind of know how many might be. So for example, if you soak in a mercury that's going to bind specifically to a sulfurs, then you know how many cysteines you have, and you can guess how many might be free cysteines, not in a disulfide, and that's going to be kind of the number you're going to be going for. So it depends on the atom type.
Okay, and then the last question that came in was, what is the minimum I over sigma, which is sufficient to solve a structure?
Yeah, and the answer to that one is going to depend on the situation. And we'll see a few examples of that. And in fact, in a slide that I'll show a little bit later, we'll show you that number varies dramatically with the atom type and the resolution that we're working with. Is there a similar planner for SIR? No. And that will be, yeah, those numbers will be different for SIR because we're going to be talking about looking for isomorphous differences instead of anomalous differences. So no, we don't have that planner. It's a good question. It would be a nice tool. Let's look at another situation. So we're gonna, a nice thing about this GUI is that you can hit the configure button, and then you can just like change one thing, and then you hit run, and then it runs the new version. So let's change our job title to erase the E after selenium and make it sulfur. And then we're gonna make that sulfur, and everything else is gonna be exactly the same, okay? Oh, let's make the wavelength different, just because for sure we wouldn't do it at that wavelength. Actually, we might, but it's pretty rare. Okay, so let's make that, we could do 1.5 or 1.8. Let's do 1.8, so we're really trying to go for a SAD experiment. Okay, so yeah, go ahead and hit run, Paul. So if you have a sulfur, what's the difference? The big difference is the F double prime, the scattering, anomalous scattering from the sulfur is much less. So in the middle line there, it says target anomalous scatterer atom S, F double prime 0.74. So remember, it was 3.8 approximately for our selenium. So we have a much smaller anomalous scattering. Just parenthetically, if we had a selenium atom, but the occupancy of that was only 0.7 over 3, like 20%, that would be just the same as this. So what matters is a high occupancy and a high scattering factor. Okay, so let's see what happens here when we do this. So if you scroll down a little bit, we can click down to 2.5. So this says, once again, they have the same number of reflections, and the I over sig I that we are going to need now is like 98, so 100 to 1, a 1% error in measurement. This will give us a half data set correlation of 0.15, pretty low, anomalous estimate of the quality of the anomalous data of 0.4, anomalous signal of 20, and still have a high chance. So in this particular case, if we have very accurate data, 1% errors, we can solve the structure with a very high certainty. So that's pretty good. We're in pretty good shape in this particular case. And even though we don't have as much scattering, if we measure the data very accurately, that's going to work. Now let's look at one more situation. So here we changed the anomalous scattering factor. Let's change instead the number of scatterers. So let's turn this into a slightly different experiment. We're going to do a bromine experiment. Sorry, we're going to do let's do a bromine experiment with RNA. And we're going to say that we somehow got one bromine on every residue. And we're going to ask the question, is this going to work? And so here we're going to have lots of scatterers, and the anomalous signal is going to be massive, or the total anomalous scattering is going to be massive. But will we solve it? Okay, so let's go. Let's make it just 50 residues, just for kicks, and RNA and bromine, and let's do this at a good wavelength of 0.9 angstroms. Should be okay. And let's hit.
We're going to use 50 bromines, right?
50 bromines. Yeah, that's like massive. Okay, let's put that in there. And what will happen? Okay, so here, if we scroll down to 2.5, we have lots of reflections, and we try to measure our data very, very accurately, 1% error. And our anomalous data has a correlation with the true answer of maybe 0.75. Notice that the half data set CC, we're calling it 99%, so that the two half data sets are exactly in agreement. So why does it say 0.75 for the estimate of how good it really is? That's because just in general, even if your anomalous data is like perfectly matched, you have systematic errors that cancel some things out. So that's just a guess. But anyways, it's very good data, but our anomalous signal is very small. It's only 4, and we'll see why in a second. And the probability of us solving this is very low, under 20%. So why is that? It's because there's so many sites. It's very hard to find them because the information per site is going to be low. Okay. Any questions? And if not, we're going to go back to slides for a moment here.
There was one question about how do you reach an I over sigma I of 98 in practice.
Yeah. So actually, Paul, I'm trying to fool with something on my computer. Can you answer that question for them? And then I'm going to see if I can get my Phenix running.
Well, you have to collect very good data, I guess, is the simple answer. Yeah, I mean, it means you have to do a very careful experiment. I think ultimately, and that I think there's a lot of factors that go into that. Beamline needs to be set up properly. Beam shape. Yes, radiation damage is going to be a problem, probably in many cases. And actually, one of the things I'd recommend is really talking to the beamline scientists about how to collect a very accurate data set on their beamline. There are things you can do, like helical data collection or translating it along a crystal. There are ways to try to minimize radiation damage. Some of these things require a small beam. So there's a very long list of things that you might want to do, and some of those will be beamline specific. The other thing is not. There's a temptation to try and get the highest resolution by putting a lot of photons through your crystal, but of course that will damage the crystal. So when you're doing the phasing, you want to resist that temptation and actually often put fewer photons to get somewhat lower resolution, but minimize the radiation damage. So it's a whole course or a whole workshop in itself is how to collect good data. I imagine there are other people on the line who have ideas as well. Do you want me to stop sharing, Tom, so you can show slides?
Yes, so let me show some slides here. Okay, great. Let's see. Is there another question there? Are we good?
So there's, well, a comment from somebody. It's surprising because I was always told that for selenium SAD you needed data better than 2 angstrom. That doesn't seem to be true.
That is correct, that it's not necessary. So selenium data, people very often solve structures with selenium where the selenium may diffract to as low as, let's say, 5 angstroms is not an uncommon situation. So yes, it's good to have high resolution data, but it's not always essential. And this little tool really will help you try to figure out whether it's necessary in your particular situation or not. So like I said, it's not uncommon to have a crystal that maybe it diffracts to 3 angstroms, maybe the selenium anomalous signal goes to 5 angstroms, you find the seleniums, you get a low resolution structure, or low resolution map, you density modify and you extend it with maybe some NCS to 3 angstroms and you solve your structure. This is not at all uncommon thing.
Sorry, I may have misspoke actually. It's sulfur SAD, not selenium SAD.
So sulfur SAD, generally that's harder and you generally need more accurate data. But the same rules are going to generally apply. You could do sulfur at low resolution, but it's very hard to get the accuracy that you need to make that work. So you can't just say, no, you have to have 2 angstrom data to solve a sulfur SAD. Not so, you can, but you do have to have very, very accurate data to solve a sulfur SAD. Okay, so let's talk about this a little bit. Give us a little bit of theory for a minute or two here in planning the experiment. Get back onto the slides. Okay, so the idea here is, what are the important things that are going to determine whether or not we're going to solve this structure? So let me just list some of them. We kind of saw them. It's like, how many sites are there? And another big one, are the sites ordered? So if you have seleniums that are in your methionines, but the methionines are disordered, then the methionines basically will diffract at very, very low resolution, but at high resolution, they'll be so disordered they won't contribute to the scattering in any substantial way. So how ordered they are is very important. What's the anomalously scattering atom? We already talked about that. So sulfur versus selenium is a big difference. What wavelength do we collect the data at? And this has two aspects. One is, are we collecting at a wavelength where the anomalously scattering atom has strong anomalous scattering? And we talked about that already. But the second aspect of wavelength is if you go to very long wavelength, then atoms that are you normally think of as non-anomalously scattering start to contribute in a substantial way. So oxygen has anomalous scattering that's substantial when you go beyond 2 angstroms wavelength. And so if you're going to collect and do an experiment where you're, for example, doing sulfur SAD, the sulfur scatters more and more as you go to long wavelength, but the other atoms start scattering more and more. And so then you have kind of a dilution of your signal. So that's also important. And then the last really big deal about whether you're finding anomalous substructure is how accurate are the data. So we talked about that we have to have 1% accuracy on data if we want to do a sulfur SAD experiment. The selenium one, a few percent accuracy is sufficient. And also, how much data do we have? So then that comes down to basically how many reflections are we measuring accurately. So when we talk about accurate data and I say 1% error, that means 1% for the whole data set, not the 1% accuracy in your low resolution shell, but 1% overall. So if you collect your data to 2.5 angstroms and you have 7,000 reflections and they're 1% accurate, that's great. Then if you go to 1.5 angstroms, you're going to have like 25 or 30,000 reflections. If you measured those, you'd have a huge amount of data. I see Nigel's getting close to screen sharing here. So the key steps. Okay, so our key steps now are, one, we want to find the substructure, and that's going to depend on the things I just talked about. In particular, the anomalous signal, which I'll define in just 1 second. And then the second set, let's go, yeah. Let's put them all up, yeah. One more, yeah. Okay, so finding the substructure, perfect, that's great, Nigel, right there. This is going to depend on what I'm going to call the anomalous signal. And basically, that is going to amount to the peak height in an anomalous difference Fourier. If we had the answer and we calculate anomalous difference Fourier, how high are those peaks in anomalous difference Fourier? So go ahead, next down. And it's going to amount to information per site. And that comes back to what we saw before about when we put in the bromines, I mean, a ton of bromines. It was a huge signal. Next slide, Nigel. It was a huge signal, but we couldn't solve the structure. And that's because the signal is diluted over this 50 different sites. So it's not that much information per site. And the answer is going to be that you're going to find your substructure if this anomalous signal is bigger than about 10. Okay, so next slide. Is the second half of it's going to be, if you find the sites, are you going to get a good map? And so these two things are not exactly the same. And how good the map is going to be is going to determine largely by how accurate your data are. And that's going to be the anomalous correlation, which is the correlation of anomalous differences with the ideal, which we talked about in our little example. Next, Nigel, go ahead. And that's going to determine how accurate the phasing is. So let's make a little formula, and you can click 5 times, Nigel, to put up all the little buttons so we can just see them all at once. So what's going to determine this S anomalous signal? So we want a big number for anomalous signal, and what's it going to be determined by? One is the anomalous correlation, how accurate the data are. That's in pink there, or in skin tone. Number of reflections, so more reflections means more data. And then skip to the bottom there, number of sites. Notice that's on the denominator. So more sites makes it harder to find the substructure. And then the last part is the
is the anomalous substructure ordered? We talked about that. And basically it comes down to a factor that says what fraction of our reflections are contributing in a substantial way. Okay, so next slide. We can simulate that, and that's what we did, and then go right on to the next slide. So we're going to have all these factors that go into it, and we can simulate the anomalous signal. Perfect. So here's what we just did a moment ago, although this happens to be 3 angstroms instead of 2.5. And I've plotted here, the x-axis is the I over sigma. So this is what we had a question about. How high does my I over sigma have to be? And this is a plot on the x-axis is how high is the I over sigma, and the y-axis is how high the anomalous signal is for this situation where we have 300 residues, 5 seleniums at the peak wavelength and to a resolution of 3 angstroms. And the number we want to shoot for here is about 10. And so we can just read off this graph that we'd have to have an I over sigma on the order of 15 or 20 for the whole data set in order to have an anomalous signal of 10, and therefore to have a pretty good chance of solving this structure. Now the next slide is the exact same thing except for sulfur. And you'll notice the curve shifts and looks a lot different. If we can go back to it, it'd be great. There we go. Now, to get up to that value of 10, we'd have to have an I over sigma I over 100. So that's just what we saw, that you have to have a much more accurate data if you have a weaker scattering, anomalously scattering atom like sulfur compared to selenium. Okay, any questions on that? Good.
There's a few questions in the chat.
Okay.
So one question was, how do we find out whether the methionines are ordered or not?
Yeah, well, that's a really good question. And basically the answer is you're going to find that out after the fact. So, but you have some things that you can go on to guess. And so one thing would be, typically your anomalously scattering atoms, if they're part of the structure itself, like if it's a selenium residue or something like that, they typically have scattering that's similar to that of the rest of the crystal, but a little bit worse on average. And that's true for both soaks, and it's true for soaks, and it's also true for like selenium, selenium methionine residues. So you basically have a really good chance of having ordered sites if your crystal diffracts well to begin with. So that's going to be the kind of bottom line here. And if your crystal doesn't diffract very well, then typically the anomalously scattering atoms are not either. But there's no sure thing on that, and it'll be a little bit of an experiment to see whether it will work. So no guarantee on that one.
Okay, and there's another question about how strong an isomorphous signal do we need to get for SIR or MIR successfully? And
yeah,
compared
so if you're
with
doing
SAD, does it require higher data accuracy?
Yeah, actually, typically it works the other way around. For data that's isomorphous differences, typically the isomorphous differences are typically very big for situations where you can realistically solve the structure. And in fact, errors in measurement can be very large in isomorphous replacement. So your typical, suppose your typical isomorphous replacement experiment is going to be something like, let's say a couple mercuries in, a few hundred or 1,000 residues. And those mercuries are going to cause isomorphous differences on the order of 20 or 25%. And maybe you have errors in measurement of 10 or 15%, and that's okay. And you'll still solve that structure. And so it's a very different situation than the selenium methionine or sulfur type situation.
Great. And then just one other one is if we have a large number of sulfurs, i.e. disulfide bonds, in this case, 56 sulfurs in 800 residues, according to the formula, we'd actually prefer to have fewer sites. Is that correct?
Well, if you have 50 sites in 800 residues, that's just what you have, right? But that'd be a great one for you to plug into that little simulator. And I think what you'll find is you're going to need pretty high resolution to solve that structure. And but that calculator will really help you try to figure out what you need to do to solve this.
And then there's a comment in here about high multiplicity helps.
Yes.
And that's true, because that gives you better data, better I over sigma I. But yes, you have to balance that against radiation damage as well. So there's a comment about.
Let me just comment on that. That's a really important point. So radiation damage, this simulator is assuming that this error that we're talking about is not systematic and includes any errors due to radiation damage. So if you have radiation damage going on in your crystal, then that's part of your error. And so if you have, and to a certain extent you can correct for radiation damage, but to a certain extent you can't. So suppose you collect your crystal way over damaged, and you have 30% radiation damage in your crystal or something like that. Then there's no way you're going to get to an error of 1% in actual estimated error in your data from such a situation. So radiation damage is part of the whole error situation. Yeah. Okay. Just to Nigel and Paul, my computer is like something very bad. So we're going to have to keep going this way for the rest of this.
Okay, we'll make it work.
Yeah. Okay. All right. So, okay. Any more questions on that?
Subject to systematic errors. What's the impact of ice rings?
Yeah. So things like ice rings, basically you want to detect this. And if we have a chance, we'll try to detect that in the experiment we're going to run in just a second here. So let's deal with that at that point. So let's go to solving our structure. And so now we need somebody, maybe Paul, if you can do it, to load up, to start our SAD experiment. So what we're going to do here is Phenix comes with tutorial data, and we're going to load some tutorial data. So we're going to click on the new project that Paul's hovering over there. So if you click on new project, it'll bring up a little window, and at the bottom of that window it says set up tutorial data. That's the one you want to click, and then it puts up a window that lets you choose a data set, and this is going to be the very first of all the data sets is the one we're going to choose. It says SAD, initiation factor, and then it'll put that by default in your documents. It's okay, it's fine, or you can choose a different place if you wish, but normally I just put it there for now. So if you just hit OK, then it will set up this tutorial data in whatever place you just agreed to put it.
Right, and just to note that there is typically a README file which you can click on, and then it'll tell you something about, Tom will explain all of this, but it'll tell you about some details about the tutorial.
Yes, exactly.
So worth reading before you try to do a tutorial, of course. And so now you should see that you have a thing that says P9 SAD, a little green check mark to say that's the current project.
Yeah, and if you click on last modified in the left-hand side in the middle, then it'll sort them on the order. And so then the one with your check mark should come up to the top. I mean, I can't see it in Paul's, but if you if you go down just above, yeah, right there to last modifying, double click on that, then it should sort them for you. Maybe, I mean, I can't see a check mark on anything.
Right. Yeah. So if you
Double-click.
click the heading
Yeah.
that says last modified, then they'll be sorted by modification. Right.
Yeah, there we go. So that's the check mark there next to P9 SAD. Perfect. So now, yeah, we're just going to click on experimental phasing, Autosol, and then that should open up an Autosol window. And just like the previous one we did with plan SAD experiment, the way this works is basically the GUI is going to give you a front page where you put in your data. And then it might have a second page where you might modify some settings, something like that. Put in a title, yeah, P9 SAD, and let's run this at 2.5 angstroms. And we're going to look for seleniums, and actually we're going to look for sulfurs too while we're at it. And then, so once we get a title in there, we're going to click on Browse for File Path, and then we're going to find our files. And since we set up tutorial data, it's going to be all right there for us. It's going to get the sequence file, and we're going to get the data file. We can do those separately or together, depending on how you want to do it. You can drag them, you can double click them, anything you want to do. We're just going to get them both in there. And then they should show up on your front page there once you get them. So,
yeah,
should,
so
if you,
some reason I can't select both files. So I'm just going to read in this SCAR file. So that's the scale pack file for those of you that are familiar with that program. But it could be an MTZ file from data processing. It could be a lot of different formats. So
yeah, in the Mac, you can't select them both. You can double click on one and then double click on the other. That should work for you.
So read in that, and I'm going to go back to browse and then read in the sequence file.
Perfect. Let's look at that sequence file with the magnifying glass that's next to it. You can click on that, and then it will just show you the contents. And you'll see the sequence file is just a string of letters. If you have multiple chains that are different, you can put them in there and separate them by a line. It'll also read FASTA format. All the standard formats will work just fine. And you can put in one copy or n copies of the sequence. It doesn't make any difference. It's going to ignore it. It's just going to take the unique part here anyways. So we can close that. And if you click on the magnifying glass for the data file, it'll just sort of summarize some characteristics of the data file. In this case, it just tells you how many data there are, tells you our unit cell, space group, stuff like that. So if you just want to check what's there, the magnifying glass is a great way to see what's there. And if you read in an MTZ type file, there would be multiple columns of data, and you would select which ones you are interested in. So we have to tell it a few more things. So notice next to the P9.SCA, it said it was a SAD-MAD peak. So it just guessed that. If it was something else, if you hold that down, there's other choices for what it could have been, and you could tell it what it was. So if you were going to read in a MAD data set, you would choose different things for each one. So this one's right, it's the SAD-MAD peak. And we need to tell it what wavelength. Oh yeah, the labels there Paul clicked on. In this case, there's only one choice. If you had an MTZ file, you might have more than one choice. Wavelength 0.9792. And the scattering factors, if you know them, you can put them in. And that's the best thing to do. Best thing is you collected your data at a synchrotron, you did a wavelength scan afterwards, on your crystal, and you ran that through Coot or some similar program, and you know these numbers and you type them in. If you don't know them, then you can ask the beamline scientist and they'll give you a good guess. If they don't do that or you didn't do it, you can just leave them blank and we'll fill in reasonable values. For SAD, it doesn't make a huge difference. For MAD phasing, it makes a much bigger difference because the differences in scattering factors are important. So we need to tell it what atom. So this is a selenium atom. We don't have to tell how many sites, and it's going to guess based on the rules I was telling you before. If it's a selenium, it's going to guess that we're talking about selenium methionine, and it's going to use the sequence file to guess that. If you put in something like iodine, mercury, it's going to guess just from typical values. and NCS copies, it's going to guess that based on the sequence file and how many copies of that sequence file fit conveniently into the asymmetric unit of your crystal, yielding a solid content of about 0.5. If you know it, you can type it in and then it will be fixed. If you don't know it, just let it guess it. It should be pretty much okay. Look also at the bottom of that screen. It gives you your unit cell and space group. By the time you get to this stage, you normally will have seen that unit cell and space group about 50 times. And so just make sure those are the right numbers and the right space group, or else you must have the wrong data in here, right? And the space group, one more thing about it is this program is going to look at that space group, and if it has an inverse, it will look at the inverse of that space group. If there are some other possibilities for this space group which you have not yet eliminated, you might need to run the program more than once. So for this particular case, we only needed to run it once. But if our space group was, for example, maybe P6, maybe P6 of 1, maybe P6 of 2, etc., because we collected it in P6, but we didn't measure any reflections along OOL, so we have no idea which one of those screw axes is present, we'd have to run it 4 times. NCS copies refers to the number of duplicates of each chain within the asymmetric unit of a crystal. So if we have non-crystal, and NCS stands for non-crystallographic symmetry. So if we have a dimer in the asymmetric unit or smallest part of the crystal, then we'd have NCS copies equals 2. Let's go to options and output, and we're going to set 2 things. The resolution, we'll set that to 2.5. Oh, 3 things. Number of processors, you might up that to, let's say, 4. It doesn't really make a huge difference in this case. But the other thing we're going to do is, so let's up that to 4. And then additional heavy atom types for phaser SAD. Let's put in S there, because this crystal has selenomethionine, but it also has sulfurs. And as we'll see in a bit, we can find those sulfurs. So I think we're all set. We can hit run and then run now. And if we typed anything in wrong, like totally making no sense, it would pop up a little error message here for us at this point. Otherwise, it's going to run and just try to solve this structure. So the thing that it's going to do is going to analyze the data, see if there's any problems. It's going to try to find the anomalously scattering sites. It's going to calculate phases. It's going to do density modification, and it'll try to build a model. It'll try to do all those things for us. And so now let's switch back to the slides if we can, Nigel, while that's running, and we'll come back to this. So
there are some questions as well.
Let's hit those first.
So somebody asked what NCS copies.
Yeah, I think
I got that one.
Okay. Can you explain a bit more about data accuracy means? What are the things which should be looking at?
Let's see. Somebody help me with the question is asking.
Can you hear me, Tom?
Yes.
Okay. Somebody was asking, what does data accuracy mean? They want to know a little bit more and what they need to look at.
Yeah. Okay. So when you collect your data, and you're going to process that data with some program, HKL or MOSFilm or something like that, and they're going to give you numbers that are going to be like as a function of resolution, basically how accurate your data are. Maybe a I over sigma, or maybe a percent error. And basically I over sigma and percent error kind of 1 over each other, right? So if you have a I over sigma of 30, then your percent error is going to be like 2 or 3%. And so you want a small percent error or a big I over sigma. Those are those things that you're looking for. And so when you collect your data, generally you're going to get a little table that shows as a function of resolution what the iris segment is, or the percent error as a function of resolution. And so in our experiment that we're talking about today, we're going to need very accurate data. And so we want typically and why do we need accurate data? Just fundamentally. So our little tool told us we need accurate data. Why is it telling us that? It's because our signal, the differences, the anomalous differences that we're measuring, they're a couple percent of the total scattering. So that means that if we want to measure anomalous differences that are like, let's say 3%, then we have to measure the data with an accuracy of like 3%, or else we have no hope of getting accurate anomalous differences. So, so this accurate data is very important in this experiment. And as I mentioned a moment ago about data that's isomorphous data, those differences are huge, like 20%, 30%. So you can have much bigger errors in your data and still get away with it in that experiment. So it's a pretty different situation. So it depends on how big the signal is we're looking for, how accurately we need to measure the data. Okay, so one source of information about that is just your tables that you're going to get from that. Also, when you run Xtriage in Phenix, that will summarize the data as a function of resolution as well. So that'll tell you a lot about how accurately measured your data has been. Now, systematic errors are a big sort of sidebar here. So if you have errors that are in your data that are systematic, they may or may not be fully represented in the estimates of error. If you measure with, suppose you did the following. Suppose you set your crystal up and you do a small rotation and you measure the data, and then you repeat that experiment exactly 500 times. Then you may measure the same data over and over again very precisely, but whatever errors are in that data might be replicated each time. For example, some reflections might have a high absorption and they might be measured inaccurately. So systematic error refers to error that if you measure the same data twice, you get the same wrong answer. And non-systematic errors are errors which, if you measure the same data twice, you'll get a random variation around the true answer. So these have two very fundamentally different properties. If you have errors that are systematic and you measure replicates of the same thing, you get the wrong answer. But very precisely, that is, you get the exact wrong answer every time. If you have errors that are more or less randomly distributed and not systematic errors, then you measure many times, you get a better answer. You get closer to the true answer. So the contrasting experiment to carry out is, instead of collecting the data from one rotation exactly the same way in a bunch of times, if you take a bunch of crystals or make the same crystal and you rotate it totally different ways, then many of the systematic errors will cancel out and you will get much more accurate overall data. So a good way to know whether your data is actually accurate is to collect it from multiple crystals, and then you average those data, and that tells you whether or not your data, how accurate the data really are. Let's see, I saw some questions fly by, but I missed it.
So yeah, Tom, there have been some questions. I want to summarize one or two of them. They're talking about low FOM. So, you know, if it's less than 0.2, should I stop, or can I do it with low figure of merit? Yeah,
so that's a really great question. And the answer is it depends. So you can have a situation where you have a very low figure of merit of phasing. So figure of merit phasing is basically an estimate based on the statistics of the phasing experiment, an estimate of how accurate those phases are. So in this experiment that we're running right now, our figure of merit from SAD phasing is going to be like 0.4. It's a very high number. On the other hand, if you had an experiment where there was one not that well ordered selenium in 500 residues, your figure of merit might be very low. But it's not a sure thing that you have to give up if you have under 0.2 figure of merit. But I'll tell you that it's relatively uncommon to be able to solve the structure if your figure of merit of phasing starts out under 0.2, but it is possible. And there are definitely cases where that can be done. And the thing that becomes important next is, suppose you have a low figure of merit. Is there a way to improve the accuracy of phasing? And what are the ways to improve the accuracy of phasing? Well, one is through non-crystallographic symmetry. Another is through density modification. And another one is if there's a lot of solvent, that's going to improve your density modification a lot. So basically, the low figure of merit, whether it's going to be a fundamental problem, is going to be determined by whether or not you're able to improve the phases afterwards. So let's go to that now. Let's go to the improving the map. So Nigel has the slide up there. Let's go down to improving. Actually, let's skip through this automated structure determination. We kind of did that already. And let's do what's a good electron density map look like, and how do we improve the quality of an electron density map? So we're going to take a few minutes to do this, and we'll do a little one of these questionnaires here right now. So let's do the next. If you click one more time, I think it should do it. Should put up two density maps. So we're going to do, yeah, there's two maps, and we're going to, the question, I think we know the answer to this first question, but we're going to, the quiz is going to be, how do you know that the map on the right is a good map and the one on the left is not a good map? So can people type into the chat just a few words about why wow, well, that you knew too much, I think, this first one. But why is the map on the right, how do you know that the map on the right is a good map and the one on the left is a bad map? And while you're thinking about that, let me just make a couple of comments.
So we've got continuous activity, solvent flat on the right, less noise on the right, clear difference between solvent and non-solvent region.
This is great.
Error is less,
Yes.
is a little bit hard to tell. Continuity, continuous chains and side chains visible in the right. Clear separation, continuous density, solvent region obvious. The density.
Perfect. Okay.
Yeah.
Perfect. These are great points and exactly right. And Nigel, if you click down, there's one more button or something, it'll put some of the ones that they said, but actually people got more than the ones I mentioned here. The main point at this, yeah, let's stop at this one. So the main point here is you can look at this, you know which one's good. And there's specific things you can say about them that let you know that one is much better than the other. So we're going to do two things with this information about, is this a good map? So right now we're going to say, this is a good map and that's not a good map. And then in a moment, we're going to say, we're going to use this information to identify how to improve the quality of a map. So let's go to the next slide. And let me just mention briefly, there's one person mentioned this one, that there's something that's not obvious about this map that you can use to identify if it's good. And it's basically the histogram of densities within that map. And the right-hand plot is a plot of value of electron density, how high the density is, and the axis is how many points in this map have that each value. And if you look at this curve carefully, you'll notice that it's not symmetric. It's skewed a little to the right. Nigel, if you click a couple times, perfect, that's great. You'll see that the most of the points are kind of in middle the value of electron density. That's where the solvent is, the places between the atoms, but then another click, Nigel. Some of the points are right on top of atoms, and they have a very high density. And this leads to a skew of the shape of this density curve. So if we click to the next slide a couple times. Yeah, sorry, one more back. You'll see two curves. And so these two curves are actually the curves that we're creating right now with our SAD phasing that we're solving a structure with. And the one on the top is actually the good one. And the one on the bottom is let me see which one's which. The one on the top is the bad one. The one on the bottom is a good one. And you can't really tell it that well by just looking at them. But if you calculate the skew of each of these, the poor map has an almost perfect Gaussian. It's symmetrical. And the good map has a slight positive skew. That's the one with the dotted lines. And so that's coming from the fact that the good map has high values that are right on top of the atoms and no very low values. And the bad map is basically random. Okay, and we can use the difference in these shapes to identify between two pretty bad maps that you look at those two, you wouldn't really know like which one's which, right? But you can tell with the skew. Actually, if you look really carefully, you'll see the one on the bottom has a flatter solvent, and also it has a little bit of connectivity in the chain that the one on the top does. So you could get it too, but the skewness is actually very powerful. So next, yeah, let's scroll through a couple of these actually, so we can do them. So we can make real maps and we can score them based on skew to see how well it really works. And the next slide. And then we can run our Autosol on each one, get calculated maps, evaluate each map with skew. Next slide. And here's our result. The x-axis here is basically how good the map really is. And the y-axis is the skew of the electron density. The colors are different resolutions. And what you can see from it is that maps that are better have a higher skew. But maps that are very bad, we talked about figure of merit of 0.2. That's very related to this number of map quality of 0.2. And if you look down there, a map that had a map quality of 0.2, so correlation to the true map of 0.2, has a skew that's almost exactly the same as a map that has a map quality of 0. So basically, if you have a really bad map, you can't tell if it's good. If it's a good map, it's totally obvious if it's good. And that's good to keep in mind, so that if it's really good, you know it. If it's really bad, it could be okay. It's certainly not really good, but you can't be sure if it's good or bad. Next slide. And this is just to say that we can use what I just said to kind of turn the situation around. You have a map, you calculate the skew of the map, and you can ask, how good is my map? Well, you can look at all the maps that we've already seen that have the same value. Let's suppose our map has 0.4 skew. Well, all the maps we've ever seen that had a 0.4 skew had a correlation to the true answer of between 0.6 and 0.7. They were great maps. So your map also is a great map. Next slide. It's just an example of doing that for a real data set. The left-hand side is different data used to solve a structure, and then how many sites are there, and then the estimated quality of the map based on this skewness. And the right-hand column is how good it really is. And so the top one with the peak, estimated quality 0.7, actual quality 0.7. So if they're good, you can tell. If you go to the bottom, or one before the bottom, it says FA inverse. It says estimated quality 0.1 plus or minus 0.4. So that's the situation where you didn't really know if it was good or not good. And so that situation comes up too. So what do we do with this information? Well, when the automated process, when it's in the middle of trying to solve a structure, it might have to make a decision. Like for this one, it's a mad experiment. Which wavelength do I use? Which ones do I include? If it's a MIR experiment, which data set do I include? For a SAD experiment, which hand of the substructure do I include? So if it's a sure thing, if one of them has a very high skew and you're sure that it's right, then you can throw the other one away. But if you're not really sure between the two, you better keep them both. So that's how that's used. Next one, Nigel. Okay, so now let's turn this around. We've found our sites, and we calculated a starting map, and we want to improve the quality of that map. We're going to use this exact same information to improve improve the quality of the map. So next slide, Nigel. Yeah, so suppose we have our experimental data and some not very good phases. We're going to get a map that's pretty bad. So that's the noisy map that Nigel's showing us. If we were able to get more accurate phases, it would look better. And so now we come back to what we were talking about before. We know a good map when we see it. So that's kind of a really important thing. And a corollary from that is if we have a little bit better map, we know that too. So that's what we're going to actually do in the next slide is, yeah, let's go to the next one if we can, Nigel. Okay. And yeah, okay. So if we saw, how do we know? Yeah, let's stop here. So I'm claiming we know a good map when we see it. And then a second aspect of this density modification, and this is just totally crucial, and it's true for crystallographic maps because they come about with pretty accurate amplitudes and not very accurate phases, that if we improve the map anywhere, that improves the map everywhere. And it's kind of a fundamental thing. So we know what's good. We know what's good if we see it. And if we can fix the map, if we can fix the phases in such a way, change the phases in such a way that one part of the map gets improved, the rest of the map is also going to be improved. So that means if we know something about one part of the map, we can use that to improve the phases, and that's going to improve the rest of the map. That's like the fundamental thing about density modification. So if you never learn anything else about density modification, remember that part, that using one information from one part of the map can improve another part of the map. Next slide, Nigel. We can, okay, so in this case, let's suppose that we were able to identify where the solvent was in our crystal. And if we don't run out of time, we'll see that in our real case, that it's very obvious where the solvent is in the SAD structure that we're solving right now. And anybody that's kind of doing this in the background, you can look at that map and you'll see, I know where the solvent is. And then we can say, okay, I figured out where the solvent is. Now in this region, I actually know something very special. I know that the solvent is very flat, and therefore that any noise I see in the solvent is reflecting something, some errors in the data or in my phases. So then you can say, let me find phases that are consistent with the experiment, any experimental phase information we came in with from our sulfur, selenium SAD experiment, and the expectation that this part of the map should be very flat. So we're going to find a kind of intersection of where the solvent becomes flat and consistent also at the same time with the experimental data. Okay, next, and we can click down on this one. And if we do that, our map becomes improved everywhere. And let's kind of go through the next couple of slides that, yeah, go on to the next one, where we do this and see how it actually really works. So this is a 1D experiment, a 1D simulation of the exact same thing. And so let's just stop here for a second. On the left-hand side, our situation is we have a protein, and that's like our peak there. It looks like a Gaussian. And then we have our solvent, and let's say that we've identified which is which in the beginning. And the idea is going to be, we're going to figure out the phase in this little thought experiment of one Fourier term using two things. One, all the other Fourier terms, and the fact that we expect the solvent to be flat. So next slide, we're going to do that. So let's take out one Fourier term from our map and then stop there for a second. And the map looks bad, right? It looks bad because we took out part of the information and there's a ripple in it. And that ripple is the term that we took out. And the question is going to be, suppose we knew the other Fourier terms exactly. Can we figure out what this Fourier term ought to look like, or what the phase of this term is? And the answer is going to be yes. So if you click once and then twice, Nigel, if we put it back in, so notice that the protein looks bad and the solvent looks bad. if we put in our term with the wrong, if we put it back in, yeah, down one, with the wrong phase, yeah, keep going, one more. If we put it in wrong, the solvent gets even worse. And the protein gets bad too, but we're not even looking at that. And then if we put it in the right phase, the solvent becomes totally flat. And then we know it's right. And the protein part magically gets better as well. Of course, it wasn't magic. It's because the phase contributes to the error or accuracy of the entire map. So next slide. So what we've done here is we've used the information about what the other phases are and the expectation that the solvent is very flat in one region to figure out the phase exactly. Now in the real world, we don't really know the other phases exactly. So there would be noise in this whole thing. And we'd have probabilities for phase information, not absolute phase information, but it's basically the same idea. So we multiply probabilities and we can get estimated phase probabilities after density modification. Next slide. So once again, the key elements, we know a good map if we see it. Improvement anywhere improves the map everywhere. And density modification fundamentally transfers information from one part of the map to another. From the fact that the solvent is flat, we improve the phases, that improves the density in the region of our protein, and therefore everything is more informative. Any questions on the density modification?
So there was a question, maybe we can answer it. Can Autosol also accommodate a molecular replacement solution into its phase determination in cases where just using some heavy atom binding sites?
Yes, so this is the experiment that's termed MR-SAD. And yes, in Autosol, you can do that in several different ways, but yes, you absolutely can. So the idea here is, let's suppose you have a molecular replacement solution for your structure, but maybe it's not that great, or you weren't able to completely complete the structure with just that molecular replacement. But your structure has, you were able to incorporate selenomethionine or some anomalously scattering atom by soak, something like that. And you collected anomalous data to go with it. So now you can combine the information that comes from having a reasonable idea of the model with the information that comes from your anomalous scattering. You can put all those together to get an improved map that you can hopefully then go on to build a model and interpret. If you do this, there's actually a couple things to think about. So you can do it totally automatically. There's a button for that in the after molecular replacement. There's a button for doing this, and you can just do it in Autosol as well. Yes. Some things to think about are your molecular replacement model is going to bias any maps that you calculate in such a way that if your model has some errors in it, then those errors might show up a little bit in your maps. And if you want to reduce that problem, you have some options. And one of them is to use that model only to find the sites, but not to calculate phases afterwards. That's an option. And you don't necessarily need to do that. But if you have problems with model bias, namely your map's looking too much like the model and not like the right answer, and then you might want to use this feature of just finding the sites with using the model MR-SAD, and then after that, calculating phases that are based only on the anomalous differences. So that's an option you have.
So then there was another question from a user who has 3 out of every 7 residues is not a natural residue, non-standard, I guess. How do you use that in Autosol? Is there a way to handle that?
Wow. So no, we don't have a, so I'm going to assume that we're talking about they're peptides, but the side chains are non-natural. Let's suppose, I'm just guessing that that's what we're talking about. So the way to handle that in the first cut of that, okay, yes, okay. So the first cut of that is just run it like normal. What'll happen is, even if you put in a sequence, you put in a sequence of something that's most similar, and then it should work reasonably well, but it won't be quite right. You have a couple options after that. One is if you don't put in a sequence, or it can't assign the sequence, what Autosol will do, or the auto building will do as well, is they'll try to put whatever residue fits the best in that location. So then you can fit things that way, and you'll get approximately the right answer. The third level is you would have to supply a new library of side chains to the program, and you don't have an easy way to do that. It can be done, but we don't have a tool for you to just supply such a thing. But all the tools are there in Phenix to take any library of anything pretty much and build such a thing. Oh, hi, Paul. Great. I'm glad you're back. So you could, in principle, do that, but there's no easy way to do that right now. You can also treat proteins as ligands. So once you have your main chain built, you could replace parts of that with with a dummy version of a protein that has your side chains affixed, and then you could fit it in that way. But we don't have a great tool for the situation you're talking about. We'd have to make something custom. So it's a great point.
So there's one more question that maybe we should try and answer. No worries. What are the values or parameters we need to see and confirm, I assume, that we have gotten a substructure solution in the Phenix log?
Yeah, so how do you know basically if it worked?
Yeah.
And what you're gonna, so the things we would look at there are generally, you're gonna look at the next level to determine whether the previous level worked. So if you can build a model, then you probably got the sites right. So it's very difficult to be really confident about whether you got the sites right if you don't do anything after that. If you don't look at a map, if you don't build a model, it's hard to be sure. The program will tell you some things to give you an idea about it. So if we have, actually, if Paul can then go back, his thing should be done, I hope. If we can go back to the Phenix GUI, we can see part of the answer to this question. And what we're going to look at is the results section of the GUI right on top there. It shows us a few things. So it says his is finished, and it says top solution, site, space group, figure of merit, Bayes CC. So the figure of merit and the Bayesian CC, those are two numbers that tell you a lot. So the figure of merit is how high the figure of merit was after phasing. And this one is 0.56, that's huge. So it would be really rare to see a number like that and it not to be right. But let's suppose that was really low, 0.18, then we wouldn't be that confident. And then we look at the Bayesian CC. That's the number, that's the estimate of phase quality that comes from the things like skew and separation of solvent and protein that we talked about before. And that number is 100 times the estimated true quality of the map. And it should agree more or less with the figure of merit. And that is telling us like what it thinks basically the figure of merit of phasing is for this heavy atom substructure, and 0.6 is very high. And so in this case, we think it's very good. If this number was a low number, then we wouldn't know for sure. And that does happen. So people send me structures they can't solve. And then I run them through, and then I look just at these numbers. And at this point, I don't know if it is solved. It's not that easy to tell. So what are you going to do next? Well, the very next thing you're going to do is you're going to look at the map. So let's look at our map. Yeah, if we go on phasing and density modification, we can look at this map two ways. First, we're going to look at just the experimental map, and this is going to remind us about finding the solvent and how bad the map is to start off with. So if we highlight a solution, in this case you don't have to, but if you highlight solution 1 under solutions, and then click view sites and map, then you get with Coot, and then it'll pop up a Coot window. You might want to change the map radius to 25 or something like that, so you can see a little bit more. And then we're gonna, once you do that, yeah, that looks good. And then we're gonna go to at the top left corner of Coot, in the middle, there's a thing that says, I can't see it right now, but I'll pull it up. We can go to select a view around a particular atom. So that,
yeah, so you can go.
so we go to
atom.
draw. Oh, okay, yeah, go to atom is fine.
Either there, it's a little yellow thing with a green arrow, or I think it's under draw as well.
And draw and go to atom is another place to find that. And then we can just choose an atom, which in this case is just the anomalously scattering atoms, which are called chain Z, and they'll be selenium atoms. If we just choose one of those and center on it, then we should see a peak at that point, and then we can look at the map around that region. So maybe we can do that.
Yeah, so that's what I'm doing right now.
Okay, so now if you zoom out, yeah, actually right where yours, you can see. So the map, if you look around there, you know, it has some connectivity. If you zoom out like Paul did, you can see there's some regions of this map that have a lot going on where the protein is. And there's some other regions that are basically just look like noise. And so that noise, that's the solvent. And we can identify that automatically by being the region where there's less going on. So we can split off solvent from protein very effectively. In particular, this case, there's 60% solvent in this structure. So it's really easy to get the solvent. And once you get the solvent, we can say, like we talked about before, in this solvent region, we're very confident that the true phases would lead to this being very flat. So that gives us a huge amount of information about what the phases must be. So then we're going to adjust those phases to make that flat and still consistent with the phases from experiment and the amplitudes we measured. And then if we go back to the Phenix GUI and click on density modified map, we can get a density modified map to pop up here. And if we maybe just turn off the experimental map, we'll see that the solvent becomes much flatter. Let's see, can we turn off the experimental one? I don't think we did.
Yeah,
There we
that's
go.
what it did.
That's that. And the solvent now looks extremely flat. Now the fact that it's flat here is not new information, right? We told it to make it flat, right? So that isn't telling us anything, but the protein is now much sharper. So if we zoom in on that location where that atom was, and we just blow it up, I think we can see. Now we should see density that looks a lot more like protein. And of course, we didn't use that information. So that's new, that's independent, that's unbiased information about what this map really should look like. So now we have a very nice electron density map. And this came mostly from the fact that we knew that the solvent was very flat. Okay, so now if we go back to the results panel in the Phenix GUI, there'll be a button for that will just show the final results in Coot. So we ran out of time here. I'm pretty sure we did. Yes. So just opening Coot button on the upper right corner there is going to open our final map and our final model. And the final map here is going to be a map that includes information from the model in the density modification. So we're going to do density modification that uses solvent flattening, namely expectation that the solvent is flat, and it's going to use the model. It's going to use expectation that the map looks something like the model, And it does this in a semi-unbiased way where it uses one place in the map to generate the expectation and about the phases, and then applies those phases in a different part of the map. And then we're going to get a composite, a density modified map out of that we're looking at. And the model that was generated here, it was generated also automatically by Autosol by using fragments from the PDB. First, big fragments to find helices and strands, and then small fragments to extend those and connect them, and then use the refinement that we'll see a lot about tomorrow to refine that model, and includes water molecules that are mostly placeholders for there is density here. The same idea that was developed a really long time ago using ARP-warp, early automatic model building. So we use that same trick to kind of mark locations of density and improve the quality of the map by putting dummy density at places where you haven't actually built anything. Okay, so this map should look pretty good at this point. If we zoom in on anything, maybe just zoom in so we can see a little bit about the density. And then we want to look at one more thing here. When we did this experiment, we had sulfur and selenium when we ran this in Autosol, and the phaser that we won't hear that much detail about experimental phasing from phaser. You'll hear about molecular placement shortly. Phaser does the phasing in this experiment, and phaser finds the sites in this experiment. The way it finds sites is it asks the question, if I put a site here, how consistent would the anomalous differences that I got from this site be with the experimental data, averaged over all possible configurations of the protein part? And the answer to that question will depend on the scattering factors for that atom. So if we have a selenium atom, it'll have one answer for how well it will fit at every place. And if you have a sulfur atom, you have a different answer for how well it'll fit at every place. So then we can estimate whether an atom at a particular location is probably a selenium or probably a sulfur. So Paul zoomed in on one here where phaser thought it was a sulfur. If we look at that carefully, we'll see that in fact, once we built the model and everything, it put a cysteine there. And in fact, so that probably was a sulfur that it found at that location, and it correctly identified that it was a sulfur and not a selenium at that location. And most of the other ones, if you go to those heavy atom sites, they're seleniums. In this experiment, there's actually one atom that it sometimes finds that's just like randomly somewhere that must be some solvent thing that I don't even know what actually is. So this didn't have really great geometry in the one Paul is showing here, so that Coot doesn't draw the bonds exactly the way you expected, but it did put a sulfur, a selenium at the location of a selenium methionine side chain. So back to answering the question about did it work? Basically, if you get a result that looks like this, there is no question, this worked, it was fine. So you go one step farther than where you're asking the question, and if that one works, then the previous one probably worked. So here we were able to build a model, and it refines well, and in fact, this has a very good R factor and everything. And so then you know that yes, the phasing worked, yes, the finding the sites worked, but when you just do one step at that point, you don't always know whether it worked. No. Okay. Any other questions left here?
There was a question here about how do we know if the data set we've collected has enough anomalous signal?
Yeah, after you collected the data, there are several things you can do that will tell you the answer to this question. So there's a program in Phenix. Maybe you can find it, Paul. It's going to be under. I'm not even positive which panel it is. But if we go to the main Phenix GUI, I think it's going to be under maps or reflection data. Look under reflection tools. We're looking for scale and merge is the one we're looking for.
Scale and merge.
Yeah.
One, yeah.
So that tool will take one or multiple data sets where you've already processed them. And you can take many crystals and you can pop them in this program, or one crystal, or multiple scans from one crystal, whatever you want. You can throw all the data in there. And what it will do is it'll split the data into half data sets, and it will analyze the anomalous differences in one half and the other half, and then it will compare them to each other and give you the half data set correlation as a function of resolution. So there's several tools that will give you this information. This is one I just wanted to mention, that this is a great tool if you have multiple crystals, for example. It knows how to merge data that has variable errors as a function of resolution in different crystals or in different parts of one crystal. So this is a way to get that half data set. Another way to get this half data set CC is just to use Xtriage on your data. Will give you the same calculation from one full process data set, provided you supply unmerged data. So now to finally answer your question, the half data set correlation as a function of resolution is a very good indicator of how strong your anomalous signal is. And your ballpark rule of thumb is your data is very useful to the resolution where the half data set CC is about 0.3, something like that. And so if your half data set CC is worse than 0.3 at all resolutions, then you're going to be not very happy. It could possibly work, but not likely. If it's at high resolution, it's 0 or 0.1, and then it goes to 0.3 at let's say 2 or 3 angstroms, and then at low resolution, it's 0.5 or 0.6. You're very happy.